In this video, we are going to look at Half-Life and Decay. So the first thing that we need to be clear on really is, what do we actually mean by exponential decay or exponential growth? Because this is a term that's misused all the time. So exponential decay or exponential growth, it means that in a fixed time, the growth, or it could equally be decay, grows by a fixed fraction. So that's not particularly helpful, especially for GCSE students. But what this really means, that in a given time, there will be a fixed rate of decay or growth. So for example, e.g., the number of something, number of bacteria, number of radioactive atoms, doubles every day. So we've got our fixed time period and our fixed rate of growth or decay. Or we could say the number triples every week. So again, we've got our fixed time period and our fixed decay. Now, there is another kind of way that we can word exponential decay or growth. We can also say the rate of decay, or equally growth, is proportional to the number of things. Okay, again, not particularly helpful on its own, but what this means is that if you have a small number of something, the rate of change will be very small. If you have a very large number of things, the rate of decay will be very, very high. So again, you can link this back to this first explanation here. So if you're doubling something every day, for example, we start with 1, we go to 2, then we go to 4, then we go to 8, 16, etc. Okay, when we only have a small number and we do a change, right, that change is quite small, right? We're going from 1 to 2 or 2 to 4. But if we have a large number of things, that change is very large, right? Because we've got this fixed fraction each time. And you could write this mathematically. You could say something like the change in a number over the change in t is proportional to the number of things itself. And if you actually do the maths, if you follow this through, you would need to do some integration, but you end up with an equation that governs exponential decay or increase, where we basically have this equation here, and then it's plus or minus depending on whether we're getting bigger or smaller. E is a number where it's 2.71, right? It's a bit like pi, it's an irrational number. T is time, n is the number you start with, n is the number at a given time, and k is the decay constant, which is the fixed probability of decay. But this is most definitely not GCSE. This is what we do in A-level physics. So on a graph, what does this look like? So we have a number of something, and we are progressing in time. And because we're talking about radiation, we're typically going to be talking about decrease. Right, if we're talking about increase, then obviously we would be increasing in the other direction. So we'd be increasing like this. All right, and that gradient gets steeper and steeper and steeper because of everything I've just said. Now, the y-axis can be labelled in a number of ways when we're talking about radiation. Right, the y-axis, it could be number of nuclei. It could be activity, which means decays per second, right? Which it could also be labelled as decays per second, or it could be labelled in becquerels, which is the unit, which again is per second. So if we said there's a radioactive source that has an activity of 10 becquerels, that would mean there were 10 decays per second. So these graphs are really important and come up every single year on GCSE exams. So spending time on these graphs, doing lots of practice on these graphs is really important. So all exponential decays or growths have this property here, as we've discussed, right? In a fixed time, the growth grows or decays by a fixed fraction. So what that means is if we take the number and then we halve that number. So let's start here with 1, 0.5, we get ourselves a t, right, a time. If we halve it again, 0.25, and then we go across, and then we go down, we get ourselves a t2. Okay, we'll do it one more time, 0.125, we go across, and we go down, and we get ourselves a third time. And we notice that all of these times are equal. Okay, this leads us to the concept of half-life, which is the time it takes for half the atoms in a sample to decay. So from this graph, we find it, we start with the full number, we halve it, we go across. This time here is our half-life. We can do it again, we can halve it again, go across, go down. This time here is our half-life. If we do it 3 times and take an average, that's even better, and we should, of course, encourage students to do that. Now, like I said, the y-axis can be labelled in a number of ways, which gives us a couple of different definitions for half-life. This does catch students out because they have to be flexible in their understanding of what the half-life means. So it could also be worded like this: the time it takes for the activity to decrease by half. Or instead of activity, it could be the number of decays per second to decrease by half, because like I said, all these things are linked. So students need to be able to find the half-life from a graph. They need to be aware that if you take multiple readings, you're going to get the same or very similar half-lives, and an average is, of course, an improvement. They need to be aware that you can label the axes in different units. And they also need to be able to answer worded questions on this, where they'll say something like the half-life of some sample is, 3 days. How long to get to 12.5% of the initial activity. Or they will say, there's so many ways they can word this. They might say something like, the initial number of nuclei is, 10,000. Okay. After a time, there were 500 nuclei. What is the half-life? Now, good students will quickly figure out quick ways of doing this. I would encourage you to teach it in a very specific way, because this is accessible to all students. Whatever the question, I would basically get them to make a kind of simple table. So I would get them to say something like number of nuclei, maybe fraction of starting nuclei, fraction of decayed nuclei, You could do it as percentage of starting nuclei. You could do percentage decayed, and then probably also number of half-lives. Now, obviously, you don't need to do every single one of these columns for every single question, right? If the question's about percentages, you're probably going to want these two columns, right? And this one. If the question is about the initial number of nuclei, you're probably going to want this column and this column, right? But by doing a table with how many columns, it really, really makes it clear. So we can start to fill it out. We're going to start obviously with one as a fraction of our nuclei, and that's obviously going to be at 0 half-life. That's going to be at the start. Okay, again, and getting students to realize this is 0 is important. So how much is going to be decayed? Nothing as a percentage, 100 and 0. After 1 half-life, we're obviously going to have 0.5, or we're going to have a half. So again, we're going to have 0.5 as decayed or a half as decayed, and then percentage-wise, 50-50. After 2 half-lives, we're going to have 0.25 left or a quarter left. We're going to have 0.75 decayed or 3/4. We're going to have 25 and 75. Okay, you can see where this is going. Okay, we'll do one more. 0.125, an eighth, 0.875, and 7/8. And then we're going to have 12.5 and 87.5%. Okay. Following this method means students can literally just have to halve things or maybe double things, and they just have to be able to count. All right. Now, obviously, if there's a number of nuclei, they will have to work with some bigger numbers. So they can, of course, use their calculator. Right. They can just put in a number of nuclei like this. And if there is a specific half-life given, in as a time in days. Okay, so for example, my example here, obviously you're going 3 days, 6 days, 9 days, 12 days, etc. So for the first question, it'd be really easy to read now. We've got 12.5%, 12 days. In the second question, we've got 500 nuclei left. Okay, so I haven't actually gone that far. I'd have to halve it again and a bit more, and then I could read across the number of days. The one thing that students get confused about that is worth taking lots of time over is they get a bit confused that, this one are halving or doubling, whereas the number of half-lives or the actual time is not halving or doubling. And you have to be really careful to explain that time is increasing linearly, it's increasing in equal steps, whereas the number or the activity is halving each time because of this definition here.